So we are dealing with analysis of simple AC circuit. When we say simple AC circuit, तो इसका मतलब ये हो गया कि अपने एक एक करके एक एक कंपोनेंट पहले लगा करके देखेंगे कि किस तरीके से सर्किट बिहेव कर रहा है, and then we will begin with the other aspects. So in the first part we are dealing with simple resistive circuit. So in a simple resistive circuit, resistor is connected across an alternating voltage or an alternating source of EMF, which we write as E is equal to E naught sin omega t, और ये हो गया कोई रेजिस्टेंस R. तो इस सर्किट के लिए अगर अपने करंट अगर फाइंड अगर करना चाहते हैं, so the alternating current can be simply written as I is equal to E upon R. So the current as a function of time is equal to E naught by R sin omega t. तो यहाँ से अपने एक बात लिखते हैं, I is equal to I naught sin omega t, where the peak value of current is equal to E naught by R. यहाँ पे अगर अपने और सारा बात अगर अपने बोले तो the first thing which I say over here is current is in phase with EMF. When I say current is in phase with EMF, तो इसका मतलब ये हो गया कि अगर अपने इसके लिए अगर ग्राफिकल रिप्रेजेंटेशन अगर बनाए of current with time and voltage with time, so the graphical representation is going to look like this. तो अगर ये अगर वोल्टेज का ग्राफ है टाइम के साथ साथ, in green we are writing E with T. So the current with time which we are drawing in blue will be in phase with the value of EMF. So it is in phase with the value of EMF, so we are getting I as T in this same way. So current and EMF both are in phase with each other. और अगर अपने फेजर एनालिसिस के हिसाब से अगर इसको समझे, तो इन फेजर एनालिसिस वी आर सेइंग दैट इफ दिस लाइन इज रिप्रेजेंटिंग एक्स एक्सिस, तो इसके ऊपर अगर अपने EMF डिपिक्ट करते हैं, if I am writing this as E naught, so the current is in phase with this, that is the current is also in the direction of E naught, तो ये हो जाएगा I naught, और इन दोनों के बीच का फेज एंगल या फेज फैक्टर जिसको अपने बोलते हैं, दैट इज 0 डिग्री. The value of resistance offered is equal to R. इसको अपने impedance भी बोल सकते हैं, that impedance of a simple resistive circuit is equal to R. Impedance of a simple resistive circuit is equal to R. In the next analysis, we are taking simple capacitive circuit. So in this case, we are only attaching a capacitor with a source of alternating voltage. Simple capacitor circuit or simple capacitive circuit. So one capacitor is connected to a source of alternating voltage, where the source of alternating voltage is written as E is equal to E naught sin omega t, and the capacitance is equal to C. तो अगर अपने इसके लिए अगर बात अगर लिखें, तो कैपेसिटर के लिए अपने लिखते हैं कि अगर किसी इंस्टेंट ऑफ टाइम पे अगर कोई चार्ज Q है, तो Q can be written as CE, and the charge as a function of time will be written as C E naught sin omega t. So from this expression, if we wish to calculate the value of current, so current can be written as I is equal to dq by dt, and on differentiating this expression we say that the current as a function of time is turning out to be C E naught omega cos omega t. So if I modify this expression of current I as a function of time in this way, E naught upon 1 by omega c, and then I'm writing it in terms of sine omega t plus pi by 2. So sine omega t plus pi by 2 can be written as cos omega t. So over here from this expression I can say the following things. The first thing which I can say is that if I compare this with this equation I E naught by R. So over here I am not using the term R, but I am using the term reactance of the capacitive circuit, and omega t plus phi. So over here I write the reactance, which is equivalent to resistance. The reactance of a purely capacitive circuit is equal to 1 by omega c, is equal to 1 by omega c. And the next thing which I can write is current leads EMF by phase factor of pi by 2. या सिंपल करंट लीड्स ईएमएफ बाई पाई बाई 2. अब अगर करंट लीड्स ईएमएफ बाई पाई बाई 2 है, तो अगर इसको अगर अपने यहाँ पे ग्राफिकली अगर समझें, so we are drawing a graphical relation between EMF with time, and we will also understand it in terms of phasor. So as a function of time, the voltage can be drawn in this way. So in blue we have drawn EMF E is equal to E naught sine omega t. And when we are drawing current, so it is sine omega t plus pi by 2. When it is sine omega t plus pi by 2, so I can say at t equal to 0, the value of current is at peak, and it is leading EMF by pi by 2. So the graph of current is going to be this. You can use a solid line as well, because we are drawing from different colors, so we can use solid line also. So this is regarded as current as a function of time, where the current is leading EMF with pi by 2. And if we draw a phasor analysis, so in a phasor analysis we are understanding it like this, that in a phasor, if I represent EMF with time over here in the form of this phasor, so this is representing E naught. So the current is leading EMF with a phase factor of plus pi by 2. And since I said that they are example of an anti-clockwise rotating vector, so the angle is an anti-clockwise sense, making a angle of pi by 2, and this is equal to I naught that we have. So in phasor analysis, we are drawing it in this way, and this is to be noted that the reactance of a simple capacitive circuit is equal to 1 by omega c. The value of 1 by omega c will be measured in ohm. It will be measured in ohm. So the reactance of the purely capacitive circuit is equal to 1 by omega c, and it is leading EMF by a phase factor of plus pi by 2. So in the next analysis, we are coming to simple inductive circuit. So this time we are dealing with simple inductive circuit. When I say a simple inductive circuit, then I mean to say somewhat like this, that here inductor of inductance L is connected to an AC source. E is equal to E naught sine omega t, and we are taking inductance as equal to L. So if we go with the equation, so I can write that E naught sine omega t is equal to L di by dt. You can also write it from the Kirchhoff's equation, E naught sine omega t minus L di by dt equal to 0. Because as the value of current will be trying to increase in this inductor, it will try to oppose So you can write it from that expression as well. And from here, we write that di is equal to E naught by N sine omega t dt, and we are integrating this expression. So if we integrate this particular expression, so we are getting it in this form that I is equal to E naught by L integration of sine is equal to minus cos omega t by omega, and we can write that I is equal to E naught by omega L with a minus sign cos omega t, and if I write it in this way, E naught by reactance due to an inductive circuit into sine omega t minus pi by 2. So from here on comparison, I can say that reactance of a purely inductive circuit is equal to omega L, and in a simple inductive circuit, in a simple inductive circuit, current lags EMF by pi by 2, or the phase factor is minus pi by 2. And now if I consider this over here in a graphical sense, so if we are drawing a variation of EMF with time, then it is making a graph like this, and the current is at a lagging behind by pi by 2. So this time the variation of current with time is going to be in this way. So variation of current with time for a purely inductive circuit is in this way. Current is lagging EMF by pi by 2. At t equal to 0, at t equal to 0, from this expression I can say that I is equal to minus E naught by omega L. So the graph is beginning at t equal to 0 from minus omega E naught by omega L over here. And if we do the phasor analysis for this particular circuit, then the current is lagging behind by pi by 2. So if this is representing EMF or E naught, so it is lagging behind, so it will be making a angle of pi by 2 in a clockwise sense, and the current is drawn over here with a value of I naught, where I naught is equal to by reactance of an inductive circuit, that is XL. So these are the three simple circuits that we have come across, that is simple resistive circuit, simple capacitive circuit, and a simple inductive circuit. So this one is a simple resistive circuit in which current and EMF are in phase with each other, and the resistance offered by this circuit is equal to R. Then we came to a simple capacitive circuit in which the reactance is equal to 1 by omega C, and the current is leading EMF by a phase factor of pi by 2. And then we read a simple inductive circuit in which the current is lagging EMF by a phase factor of minus pi by 2, and the reactance of the purely inductive circuit is equal to omega L. So now we are taking example of a circuit in which we are involving more of the components. That is, you can take one at a time or two at a time. We have taken one at a time. I am taking all three at a time, and then after the analysis, you will be knowing what to do when only two of them are involved. Or while problem solving, we will take two at a time. So let us consider a NCR series circuit. So we are doing analysis for a LCR series circuit. So when I talk about a LCR series circuit, then we are connecting a inductor, a capacitor, and a resistor across an alternating voltage E is equal to E naught sine omega t, and inductance is equal to L, capacitance is equal to C, and resistance is equal to R. So if I write the reactance which each of them is going to offer, so the reactance which each of them is going to offer can be written in this way. So this is equal to omega L. For a capacitor it is going to be 1 by omega C, and for a resistor it is going to be R. So these are the reactance which is offered by each one of them. The combined resistance of them is regarded as impedance. The combined resistance is regarded as impedance. When we talk about impedance of a purely resistive circuit, then it is equal to R. The impedance of a purely capacitive circuit is equal to 1 by omega C. The impedance of a purely inductive circuit is equal to omega L. But over here, if we do the analysis and calculate the impedance which is offered by the three of them combined, so in order to do this, we are doing a phasor analysis. So in a phasor analysis, we are considering something like this. So we are considering something like this. So the reactance which is offered by the resistance is in phase with EMF. So I write over here R. So this line over here is representing the EMF, that is E naught. Now for a purely resistive circuit, the current and EMF are in phase with each other. So the resistance which is offered by a pure resistor is in phase with EMF E naught. For the capacitive circuit, it is going to lead by pi by 2. So it is going to lead by pi by 2, which we are marking as 1 by omega C. For an inductive circuit, it is going to lag behind by pi by 2, which we are writing as omega L. Now in majority of the circuit, 1 by omega C is greater than omega L. 1 by omega C is greater than omega L. And hence I am drawing their resultant over here as a solid black dot over here, which we are writing as 1 by omega C minus omega N. And the resultant of the resistance over here and the reactance of capacitor and inductor combined is giving us an impedance in this direction, which we are writing as Z. So this is the impedance offered by the circuit, and the net impedance is making an angle phi with the direction of EMF E naught. So if I write the value of Z, so the value of Z is written as 1 by omega c minus omega L square plus R square का square root, and the value of phi can be written as tan phi is equal to 1 by omega c minus omega L upon R. So this is the value of the impedance which is offered by the circuit, and this is the phase factor angle that we have calculated. And the equation of current will now be written as I is equal to E naught by Z sine omega t plus phi. So if this phi wouldn't be in this side, that is in the anti-clockwise sense, if it would be in the clockwise sense, then we would have written over here minus phi. So since it is in anti-clockwise sense, we are writing plus phi, and the expression for current can be written as I is equal to E naught upon 1 by omega c minus omega L square plus R square का square root sine omega t plus phi. So we obtain a expression like this for the value of current in an LCR circuit. In an LCR series circuit, we are obtaining the equation of current like this: E naught upon 1 by omega c minus omega L whole square plus R square and sine omega t plus phi. So now what we are going to do is we are going to analyze this expression of current that we have, and we are saying that the value of current is going to fluctuate with the value of omega. That is, if we vary the angular frequency omega of the AC source, the peak current is also changing. So I am writing over here that the peak value of current I naught will vary with angular frequency omega, because it is obtained in this term that I naught is equal to E naught upon 1 by omega c minus omega L square plus R square का square root. So we have obtained an expression like this, and I am saying that with omega the value of I naught is also varied, and I naught will be maximum. I naught will be maximum when the denominator is going to be minimum. So the minimum value of a square function, that is 1 minus omega L, 1 by omega c minus omega L is equal to 0, and hence I write that for omega that is equal to 1 by root over LC, the value of I naught will be maximum, and this is regarded as the resonant frequency, and this is regarded as the resonant angular frequency, and the corresponding frequency can be written as 2 pi by omega, that is 2 pi root over LC. So this is the value of 1 minute, made a mistake I guess. So we can say that omega is equal to 2 pi f, and hence the value of resonant frequency will be omega by 2 pi. So 1 by 2 pi root over LC. This is regarded as the value of resonant frequency, and omega is equal to 1 by root LC is the corresponding value of angular frequency. That is, at this value of f, or this value of omega, the value of peak current will be maximum. The value of peak current will be maximum. So in the next session, we will be beginning with the study of variation of I with omega, and we will try to analyze the peak of the graph.